All right, Michaela, take us away.
Okay, so like I think the main thing that like we wanted feedback on was like in one of the previous composability syncs we talked about like the potential like desugaring approach for nested tensors, and then one thing that came up was like a lot of the time like nested ops actually like are essentially dense ops and like how to best exploit that, right? So like I mean, first let me just give like a 20-second like recap of what nested tensor is. So like it's a list of tensors, same like number of dimensions, D-type device, but like different sizes. And then like metadata size is a tensor, which is like a list of sizes of the tensors. Same for strides. And then there's like offsets, which is the start of each tensor. And then like the conventional like tensor nt dot size, tensor dot size and tensor dot strides just like errors out for nested tensor, which like breaks with a lot of like things. And for nested tensors, like in PT2, it's like very closely tied with dynamic shapes, I think, because like the sequence lengths, for example, in the B star D case, which is like batch size, sequence length, embedding dimension, the sequence lengths will change in every batch. And then the FBGEM like jagged tensor case is the case when the NT nested tensor size is like this B star D case. Um, yeah, so as a first step for now, like I added like graph breaking in Dynamo whenever it encounters like nested tensors and like nested tensor constructors, things like that. And but that was just like very much a first step that is going to be removed. And then for the part like where we want to like exploit inductors current functionality, um I think the very first step is like we need to enable tracing of nested tensors with Dynamo. So like some questions here are whether we can like reuse the current like variable builder tracing infra if like we eventually want to like make these nested ops into dense ops where like I guess the sizes and strides of the nested tensor, I'm not sure whether they need to be traced because we are like as you'll see later, we're trying to reuse like the dense infra. So what we want to do is like for just to give an example of like an op where this would happen. So like if you do like let's say an element wise op on a nested tensor, it is like equivalent to doing an element wise op on like the dense tensor where you have kind of like concatenated the first dimension of the nested tensor. So like it becomes a 2D tensor of like shape like sum of sequence lengths D from like B star D. So like what we want to do is like in the cases where you can reuse the dense infra, we want to like detect nodes in the FX graph which are doing like one of these ops, and then we want to replace that with like nodes that correspond to this chunk of code that I'm highlighting. So like essentially get the size, get the buffer of the nested tensor, view it as a 2D tensor, do the op, and then after that, view it as a nested tensor again. And then so when you have like multiple ops that are fusible, you'll have like this chunk in the middle, which is like taking the tensor and viewing it as a nested tensor, getting the size again, and then viewing as a dense tensor again. And then we want to like teach the compiler to like remove these chunks. And I think like some places that we have identified that this could potentially happen would be either in like the dynamo optimizations or in like the inductor overrides. So like feedback on like whether those are like good places to do this would be like very much appreciated. And yeah, so overall we want like the final like FX graph to like correspond to this like chunk of code, if that makes sense. Yeah, that was actually pretty much it. So like if there's any feedback, comments, that'd be very much appreciated.
Comments from the room.
I'm curious how much effort it is to like have decompositions that will work with nested tensor because like we're running into similar issues with like I think
Kan ook heel
sparse
different things.
tensors not working with decomposition. So it'd be cool if like I don't know to what extent it's possible, but yeah, for our decompositions to work more generally for other like tensor subclasses. Like I know with decompositions, we do some amount of work to make it so that they work with like general torch subclasses as far as like not calling item and things like that. But I don't know, just an aside, I guess.
To add on to Elias's comment, it's nice to like sort of compare this with what happened with Jagged Tensor. And with Jagged Tensor, in fact, I don't believe there would be any for the for the operations that can be implemented densely. And Jagged Tensor folks, correct me if I'm wrong. There wouldn't actually be any like weird operations like nested view from buffer. They have a Jagged Tensor is just tensors under the hood, so you just like do the dense op on the tensor, and that's what it will show up with, and you actually don't need to do anything in that particular case.
So are you saying it might be better to like special case under the hood for like nested tensors itself to be a tensor under certain conditions?
I don't have a particular proposal yet, but I'm just sort of trying to like generate thoughts from the room.
And you will still have to regenerate an actual jagged tensor after you do your dense operation, no?
Yeah, you do need to unwrap it and then to wrap it again, but still it means that inductor won't see a weird nested view from buffer operations that will be need to remove later. All inductor will see is usual operations on usual striated tensors.
So, but correct me if I'm wrong, but what we've seen net Jagged tensor being used at in the context of Torch compiler at the moment is, operate people decomposing it into values and offsets, passing it into their model, and then operating on those values and offset tensors separately, like not through a Jagged tensor API, but by passing those components into FBGEM kernels, which Torch compiler then ignores. So if Jagged tensor wants to be used as a construct itself by Torch compile, right? Since it lives in Torch reg, there has to be like an API and all these kind of things. So like you can only use it in a decomposed manner under Torch compile because as a data structure, it wasn't registered in core.
I think this touches on something I mentioned a while back, and I think based on some of Horace's ideas, which is like if we ever want to reconcile nested and jagged tensor, we may have to offer an abstraction from our layer that both fit into, and then we just teach the compiler how to work with that abstraction. And then there's some front end component or decomp or registration component that turns one into the other, maybe even in Dynamo.
Yeah, so what we had long conversations about that, and the idea was to use Jagged tensor in like a particular sort of a distributed context, which is where it shines, and then use nested tensor as a UX. In particular, when we then say Jagged tensor, we mean like the FBGEM kernels. And so we can call into those too, like nested tensors can also have offsets, and it can specialize and use FBGEM kernels. So this is kind of the idea here. Like we're kind of recognizing when nested tensors can be converted to dense tensors or dense tensors in certain shapes, or with certain pieces of its metadata. And then in turn, it can call into either it can just reuse the existing dense inductor compiler techniques, or it can call into like FBGEM routines and things like that.
Okay, Mengshi, at risk of putting you on the spot, do you think it would be a good time to sort of talk about like sort of the compilation regime for jagged tensors? Just to like give a point of comparison for the room, and we can also talk about the stuff we talked about in our call a few weeks ago, namely fusing the packing operation with pointwise operations after that. Do you think we can talk a little bit about that? I want to return to Michaela's doc, but I'm thinking maybe this will help also add to the discussion.
Okay, I think one of the problems I would like to point out is kind of like in the current internal models, I think we highly use the talk track thing and also with directly calling to the FBGM. I just want to know like if we support nested tensor, do we also want to support like jagged tensor into the PT2 stack so that we can massage the internal model back to the internal model, or
just so we don't have to go into that and repeat it again. If we look at the PT2 roadmap, we'll see that it's unifying jagged tensor and nested tensor kernels behind nested tensor UX.
Okay, does it mean like we should like ask the model person to write using nested tensor?
Correct.
Okay, got it. Okay.
But that also implies that nested tensor UX will preserve the current jagged tensor performance, right? Because
yes,
models rely on it.
And so part of this document that Michaela has here is a discussion of how we can achieve that. And one way in which to achieve it is by decomposing into regular dense tensors. And this is already what we do for many of the kernel implementations for nested tensors. One example. Another way in which we can do it for the cases for which you cannot convert it into regular dense tensors, right? Which would be the same situation in jagged tensor, like it's the same thing for like certain irregular shapes you can't convert to regular dense tensors. For those we call into FBGM kernels, or for those we teach inductor how to generate efficient Triton code.
But like you are already decomposing in C++, so the problem is that Python dispatch tracer doesn't see it. If we could somehow create the same infra in Python, that shouldn't be too hard, and we would just see the dense ops, and inductor will just hit it off from there.
That's a great idea. If we can trace through, if we can make those all composite, right? What would the trace look like? I mean, a trace would look like, here's your buffer, here's the function, and then there's going to be some view this buffer as nested tensor again thing. So like the trace that Michaela has in her doc, I think is the trace we would see. Like these functions already are composite.
As long as we preserve the correct data flow of the backend storage, inductor should just be able to work out of the box.
But
I'm hopeful about that.
We want to cancel out though the like get the buffer, do the operation, view the buffer as a nested tensor, take that nested tensor, view it as a buffer again, right? Like we want to be able to cancel out these, those two lines right there, the nested tensor and then view the nested tensor as a buffer again.
If you are tracing through, hopefully that would just resolve to the same variable that you are going to be.
So who's sharing? Are you sharing the screen?
Michaela,
can you just highlight? Can you just highlight those two lines right there, like the nested? Oh, those three lines. Yeah. How do we eliminate those?
Let me try to say what I think Natalia is trying to say, which is that when I put on my jagged tensor hat and I'm like, well, what is jagged tensor? Jagged tensor is not actually a tensor, right? Like by the time we get to torch.compile, it's only dense tensors everywhere. So in my jagged tensor universe, what I expect to see in the trace that I give to torch.compile is I never expect to see nested view from buffer. And I never expect to see NT buffer view.
No, I agree. So, but here's the thing. There is no jagged tensor in the dense part of the model that we're looking at. That model gets the values and the offsets. And then the people are calling into FBGM kernels like torch, ops, FBGM, blah, 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 directly. Yeah. So they've done the decomposition manually, and then they are calling the kernels manually. That's not great UX.
Yeah, and we are even doing the fusion manually.
Yeah, exactly. And you're doing the fusion manually. So we don't want that. We just want you want to be able to take a nested tensor in your dense model, like do things with it, and then compile the whole thing. The compiler will trace through the operations. The trace that comes out of it is this, like, even if it was a jagged tensor, it would be the same thing. you would see the same thing. You would see a thing that pulls the values and offsets out of the Jagged tensor, calls the kernel, and then puts the resulting values and offsets back into a Jagged tensor, right? So like we don't have to call it, we don't have to do NT-buffer view. We can give it some other name like my super special reconstruct nested tensor from blah 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 thing. But Dynamo will still need to filter these out in order to actually do fusion, I think.
Okay, so I think it's just a terminological confusion right now. So let me see if I can resolve this. Okay, so let's just talk about the pipeline for a moment. I'm gonna edit your doc, Michaela. Actually, no, I'm not gonna edit your doc. So if we just talk about the compiler pipeline, right? We have various differing IRs at different stages, right? So Torch Dynamo produces an IR that has a bunch of Torch op calls, and then AOT Autograd produces an IR that has a bunch of A10 op calls, right? Only dense tensors here. Let's just imagine that for a moment. Whereas the Torch op calls, can the Torch op calls have non-dense tensors in them?
The torch op calls don't care. You are just calling a torch op on the inputs, and it can be any subclass.
Yeah. Although I think torch function should have been eliminated at this point. If Torch Dynamo knows about torch function, it does eliminate that. But it can be a other subclass. Okay, so when we talk about traces, we have to talk about what the IR in question is, right? So the IR in question here, because there's a nested view from buffer, I believe this is referring to the torch op calls. So IR that has calls to nested view from buffer is this IR. And Christian, in the doc, and Michaela in the doc, you've proposed the way to optimize it is simply by having a pass which will remove consecutive view from buffer nested tensor size operations. This is certainly a reasonable way to go about doing the optimization if you're doing the optimization directly on Torch Dynamo's produced IR, but that's actually not the strategy the PT2 compiler does. The Torch op calls have a bunch of random stuff. They're not normalized at all. And the way we actually get rid of them is we first trace through them. And the tracing mechanism is preferred if you don't need to change autograd with your optimization. Actually, this is a good segue into the other topic, which we're not going to get to, which is pre-autograd makeFX tracing, which is talking about normalizing IR when you want to do optimizations that have autograd effects. But assuming we don't need to change autograd, actually, I don't know if that's true, actually. So we may have to open this up. But assuming we don't need to change autograd, the normal thing to do when you have this IR is we do a tracing. And the claim that Natalia and I are making is after tracing, because we only have dense tensors, we have already eliminated calls to nested view from buffer.
Okay, which part does that elimination?
So this is mostly proxy tensor tracing, aka makeFX. And what does it do? Well, it gets through all of the dispatcher stack, and eventually for each of the operator calls we actually do, that is what we actually record to the graph. So even if your decomposition is written in C++, as long as it's over the proxy tensors that we're tracing, aka the underlying dense tensors, then we will be able to eliminate them from the trace.
Wait, sorry, can I clarify one thing?
Yes.
I think what I was trying to say in the doc is for example, if your PyTorch code is let's say torch.relu NT and torch.10h NT, then I think we wanted to make that into four nodes, which is get the sizes, view as 2D, then a 10h on the dense, and then nested view from buffer. So I think the nested view from buffer, we weren't saying that it was traced from the internals of 10h or ReLU. I think we were trying to say add those nodes and then in one compiler pass and then remove them in another compiler pass. Like, I'm not sure whether I'm just like misunderstanding like
No,
everything.
but I don't think you are misunderstanding it. Like that was definitely what the approach we talked about. But what Ed is saying is that's a very good point. Is we can get those 4 nodes by implementing ReLU in that way. In fact, it already has been implemented in that way. And if we make that implementation composite, then this will work.
Oh, okay, got it.
We might actually already be at the point. So like that first part of our proposal has kind of already been implemented as long as we make our C++ operations traceable.
Sorry, you mean the step one?
No, first part of step 2, which is generating the, nested tensor, the buffer view, calling the function. Yeah, exactly.
Does that mean registering decomps? Is that how that would look?
No, I think it's as long as the functions that we have for nested tensors are composite, it will just trace through them.
Making those functions composite, they probably aren't now. So they are traced as whole.
How do we make this composite?
Yeah, actually, I'm confused because the phrasing here is replace nodes in fx graph, which suggests to me that you implemented an fx pass. And that
no, but you suggested to make them composite so that we can generate this trace,
okay,
right?
So it is being done by making them composite?
Well, this could be a way in which it can be achieved. I think that is the right way to achieve it. Because like the way we currently implement ReLU for nested tensor, it is, already composite.
Let me think. So I'm going to go further, right? So certainly, if you make this composite, then one possible decomposition is into these operations. However, and let's just think about the invariance, right? The invariance says that by the time you have gotten to pass AOT autograd, there are only dense tensors in your graph. So this is not even far enough. This needs to decompose even more. That's the claim.
Why does it have to be decomposed even more?
Because as it stands right now, there are nested tensors in the graph.
No, SZ, like nested tensor size, SZ, that's a tensor. And then nt.buffer.view and so on and so forth. T, that's also a tensor. Those are those are
but
both
nested view from buffer is a nested tensor.
Yes.
Yeah.
It has to be, because otherwise the implementation of tanh can't return.
Okay, so I think this is another explaining moment. So I want to just talk a little bit about the general context for how subclasses in PT2 might work. So let me think. So where do I want to start? Okay, so there's this interesting problem, which is suppose that you want to pass a tensor to the compiler, and the user provided tensor is some sort of tensor subclass, and the output of PyTorch compile should be some sort of tensor subclass. So in the example here, the input is a nested tensor, the output should be a nested tensor. And so you might think to yourself, oh no, then that means my compiler needs to know how to deal with nested tensor input and nested tensor output, because otherwise, how am I going to actually fulfill my API contract? And the answer is actually in PT2, no, that's not necessary, because there's a translation layer. Oh, please don't restart on me. Okay, so the translation layer works like this, right? So if you have a nested tensor as input, something needs to happen, and you need to end up with a dense tensor, which then actually goes to the compiler, compiled function, which produces some dense tensors. And eventually some more magic happens, and then you end up with a nested tensor again. And so what this ... is what we call AOT dispatch. Well, it's called AOT autograd today in the code, but a lot of the files are named AOT dispatch to sort of make it clear, and this is important for our case, that it's not autograd specific. So AOT dispatch is not compiled code. The compiler knows nothing about it, but its responsibility is to take an arbitrary tensor subclass, so that could be nested tensor, Today, it's actually autograd, because autograd tensors are like weird and special. They aren't just dense tensors. They have all sorts of extra metadata like grad functions and view metadata and things like that, which once again our compilers are blissfully ignorant of. And what it does is it does the unwrapping into the underlying dense tensor, and then calls the real compiled function, and then once it gets back the dense tensors, rewraps them into the subclass, or putting on the grad function or the other data that it needs, so that it looks like a nested tensor or a differentiable tensor once it comes out. So this is the component that would be responsible for that, as the way PyTorch 2 is designed today. Like, obviously we could debate if this is the right design or not, but that's certainly how things work today. Tris.
I don't want to break the invariant, but I could imagine a subclass that could not be converted to a dense tensor. What did we do?
That's a great question. Horace, did you want to answer that question?
Or I guess I'll answer that. So it's true that not all tensors can be converted, or in some sense, most tensors can be converted to dense tensor operations with the appropriate operators. And that, like, our underlying data representation is completely dense. So, if you're willing to, you can convert like sparse tensors or whatever into like the underlying dense buffers, and then the associated sparse MM operations on them. That being said, it's not always clear whether this is like the right option to do. And I guess it's also kind of coming back to that sort of thing, which is that it's possible that the reason why AOT autograd does this is we need to decide what parts go into the compiler and what parts, or what behavior can the compiler handle and what behavior is a compiler remain ignorant of. And the advantage of tracing through into the dense operations is that the compiler does not need to handle anything other than dense operations. But the disadvantage is that you lose the structure that you might have in the tensor subclass. So I remember, I think in previous conversations, actually, and I guess Natalia might also comment on this, I thought we were kind of leaning towards just representing nested tensors fully in inductor, and then compiling it that way.
Yeah, I that's true. That's like the end goal, but we can't just jump there. So like an intermediate.
I'd also
go ahead.
For Jagged tensor, I don't think we can do it that way, right? / we don't want to do it that way.
Or you're saying from how Jagged tensor is currently implemented, and that is not a tensor subclass of any kind?
Yes.
Or so it's more that we can't do it that way in Jagged tensor, right? Because we don't have any, or at least we don't really have the ability to trace through the underlying operations, or trace the Jagged tensor as a whole.
Yes. Christian, sorry I talked over you. Did you want to finish your thought?
Sorry, I was just saying yeah, that's what we want. That's where we want to get to eventually. But as an intermediate, this is just so Michaela has been, for example, she figured out how to make it just graph break on nested tensors. So that's cool. So someone can slap torch compile on their model, and at least it won't spit up in their face and say this doesn't work at all, right? And so now the next step is what we recognize for a lot of operations, and in fact we currently already implement, and for a lot of interesting nested tensor, or for a good amount of interesting nested tensor shapes and operators, we can just convert it to dense tensors. And we also see that it's really hard to teach inductor about, at least getting to the point where we can teach inductor about nested tensors might still take some more time. So maybe as a first step, we'll convert nested tensors to dense tensors. And then at least we'll get some gains from torch compile. Making it work with torch compile is easy if you just ignore it and you just graph break and nothing happens. But getting some gains out of it.
Well, that's really easy for pointwise operations, and you'll get a lot of mileage from pointwise operations alone. But once you want to start reductions over some dimensions, just
Yes,
doing
exactly.
them as dense ops won't bring you good perf.
It will give
Right.
us pointwise operations like layer norm and ReLU, and it will give us also linear.
Nested tensors support autograd, right?
Yes.
Brian?
Brian, I think you're muted.
Sorry. If we're saying that decomposing or desugaring to dense hops is like a nice intermediate state that gives us most of the gains, and then like getting all the perf gains actually requires inductor understanding nested tensor, I guess I wonder, like, there's a bunch of places that we could choose to implement that desugaring, where like AOT dispatch is one of them. An alternative would be implementing the desugaring directly in inductor. And I'd be curious, like, which of those two things is harder, because it seems like implementing the desugaring directly in inductor would be like more closely aligned with the end goal of inductor directly handling nested tensors.
I think, to be honest, like if I were to implement desugaring in inductor, I would do it the same way I would do it in like AOT dispatch, which is I would just use like makefx to trace it out, but just at the inductor level. So arguably, it's morally the same thing.
But does that bake in how we represent nested tensor to inductor, which may be a good thing to figure out, but.
It would bake in, so if you will want to change your internal representation, you'd need to go into inductor, and arguably inductor shouldn't care. Inductor is a compiler that works on dense tensors currently.
I have a couple other questions, which is like how, and probably Ed knows, like how would fake tensors work with this, or like functionalization or things like that?
So we covered this in the previous meeting, but the recap is when you are backed by dense tensors, you replace the dense tensors with fake tensors, and everything is fine. When you don't, then you need to natively teach the nested tensor how to be fake. So for example, I did this with sparse tensors. Sparse tensors used to not support meta device, and now they do, and it's just a little bit of annoying manual code you have to write. We know how to do it, but it's manual.
Okay, so like I know that Michaela has tried teaching fake tensors about nested tensors by like adding properties and things like that. So okay, which path should we take? Should we first do it at the AOT dispatch level? And then where do we store the decompositions? Like, do we start making tanh and all these ops composite? Can we make them composite for nested tensors only? I don't think we can, right?
We kind of can.
We kind of can.
There is like a dispatch key for nested tensors composite that Brian knows what I'm talking about. It's like a whole thing.
But could you just register Python decompositions for them and not mess around with?
I think I like that.
Cool. So
you could register that for nested tensor key only, right? So that will be fine.
All right. So that is an AOT dispatch thing, right? Like the Python decompositions. So or not?
More of like a proxy tensor thing, I think. Technically than AOT dispatch, but yeah, I think so.
Cool. So should we just register a whole bunch of decompositions? Like whenever, effectively, it's like whenever a decomposition hits a nested tensor, it will just be, or like any nested tensor should be decomposed. If there does not exist a decomposition for it, it will error out, and it will graph break, effectively. Well, how's that sound?
Yep. Like that will give you the functions for which you can easily create decompositions, which will be all pointwise.
All right, actually, sorry, I lied. I think that the decompositions do need to be in C++. Or I mean, they can be in Python, but they need to be registered through the dispatcher. I don't think we can like reapply the decompositions at proxy tensor level.
Yeah, they
So-
need to be registered through the dispatcher, yeah. But that can be done from Python, so.
Okay,
Yeah.
that's cool. So we can like recycle the C++ code we already have that already does decompositions.
Yes,
So-
I think so.
So we should probably work on that first.
And in general, like it should be possible to recycle the C++ code because the reason why our stack is designed in this way is because we wanted to reuse the C++ AutoGrad code instead of having to rewrite it in Python.
Right.
So like it's definitely the same motivation. Dark Ritual.
Yeah, just one thing I want you to bring up is for the going back and forth between nested tensor, I think the important point to not have this mixed graph is to make sure the proxy tensor is applied at the right level. And in particular, when you want to do the desugaring, we need to make sure that the underlying buffer is the proxy tensor. And so what AOT AutoGrad will trace if whatever happens to the buffer. And so naturally, all the nested tensor related stuff will disappear when you apply AOT dispatch. And only the things happening to the buffer will remain.
That sounds right to me.
Right. So I guess maybe as like concrete, like the thing I would like to see is you take a function that takes in the underlying buffers, calls like create nested tensor on those buffers, which I assume will be like an A10 op that's probably composite. You do some like operations on those, and then you I guess desugar at the end, and then you should be able to make effects through that function, and get a graph with all the get a graph with all the appropriate operators. But without nested tensor. Wait, sorry. I guess another like clarification. This does mean that we're going to need to implement every single as like a decomposition, right? Like including presumably, I don't know if you guys have like a nested softmax operation. Like that will need to be like an A10 op that we trace out, I assume.
Well, so this would be a first step, right? Like we will eventually need to teach more and more of the stack about nested tensor, in particular softmax. One thing you can always do is like you just don't allow fusions, and then you graph break, and we have an eager mode implementation for something like softmax. But if we want to fuse everything, eventually we'll have to just like keep on pushing this further and further into the stack.
Right, but I'm saying like under like the current description, what we would do, like basically nothing below or nothing at like proxy tensor or below will have any notion of what a nested tensor is, right?
As this like very, very next step, yeah.
Okay.
And so, it's easy, I think. Like, it seems relatively straightforward. It allows us to already get some fusions, which is nice. And it will work with touch compile. Like, the user at least won't see errors popping up.
Chris.
Okay. So there's also like fire alarm testing, like at the perfect time. So sorry if you hear that. Let's say I had a string of like pointwise operations on a nested tensor. I call torch compile on that function. If we have registered decompositions, like in my mind, at some point you're going to get the pairs of two dense, do the operation from dense to NT. I'm assuming at some point in the stack, you have to write an FX pass that does like the parentheses.
I think we wouldn't see the two dense or from dense to NT operations.
Where do you remove that? Where do you do the parentheses matching and remove those, I guess?
Or you don't need to do the, or sorry, if my understanding is correct, we don't need to do the, like, we don't need to do this parentheses matching because the from dense to NT, like, is kind of happening above, like, the proxy tensor level. I guess you could kind of imagine it as, like, creating a tuple and then unpacking the tuple. Where like you're tracing the operation that the objects inside of the tuple, So even though you're creating the tuple, which is your nested tensor, like
Sorry,
that
just to to make it work, we don't have to do it, but to actually make it performant, to get diffusions, we have to remove those, right? Because
no,
only
I'm saying like those wouldn't even exist at the proxy tensor level.
To answer Driss's question more directly, the thing that does parentheses matching is AOT dispatch.
And so it's like writing an FX pass in AOT dispatch to do that.
No, AOT dispatch doesn't do an FX. You don't need a graph transformation to do this.
Because there will be cases where like you can't remove them, and there will be cases where you can, and those will very much depend on the shape, right? If it's just sequences of pointwise operations, yes. But if it's something else followed by something else, where like you need to kind of keep that information around. Anyway, we'll take a look.
Or sorry, like you're saying there's information in the nested tensor beyond like what the dense operations contain, and those cannot be encoded into the op itself.
No, I'm not saying that. We can fully decompose it into its metadata, and these can all be regular dense tensors.
Okay, sorry.
So what are you saying, Christian, then?
What I'm saying is, okay, if we go back to Michaela's document, right? And we look into that, the consecutive fusible ops. It still comes down to, okay, so we will get, after the decompositions ran, this is what Dynamo, like AOT dispatch will see, correct?
No, I don't think that's correct. I think the idea, Christian, is that when you enter AOT dispatch, you will create the proxy tensor that is what is doing the tracing. And during that creation, you would do one call to get buffer. And now the only thing that gets traced is the buffer associated with the nested tensor. And so when you run the decomposition, you will do this series of functions. But because the only thing that generates graph is the buffer itself, the only thing that will end up in the final graph is the call to 10H.
Okay, that makes sense.
Boss.
Yeah, really quick question. We sort of talked about this a while back, but are we okay to completely shed the outer structure, or do we need some bookkeeping that this did indeed come from a nested/jagged structure? Do you have any thoughts on that, Horace or Alvin?
I think in this first iteration, the idea is that we can completely shed it. That we care about the case where we can do so.
Okay, I'm going to take...
You're muted, Chris.
I'm just... no.
Okay, I'm going to take advantage of the lull in the conversation to summarize what we have discussed so far. Okay, so the summary is in a few parts. So part one is long term, we agree inductor will natively understand what nested tensor is. However, in the short term, we want to get wins from inductor where no special understanding about nestedness, jaggedness is necessary, e.g. pointwise fusion. To do this, we will support compiling nested tensor via lowering to dense tensors. Sound okay? One thing I'll editorialize here is that this is consistent with jagged tensor, which doesn't have any subclass at all. So the stack for inductor that does this also works for jagged tensor.
Which is nice.
Okay, part two. How are we going to do this? The way we are going to do this is by modifying AOT dispatch to understand nested tensor. So there are a few parts to this. So one is AOT dispatch can handle inputs that are nested tensor. What it will do with them is it will unpack them to buffers, treat them as the proxy tensors to be traced, and then before calling the user function, which is calling NT-ops, rewrap them back into nested tensor. Because the like user callable that we are tracing is just got a bunch of, you know, nested tensor tanh nested tensor value calls. So we need to actually like put them back into nested tensor. This implies that nested tensor will support a tensor subclass as its buffer, and so we can interpose it with a fake tensor. On exit, we rewrap the dense buffers into nested tensors to be returned to the user. Any questions about this step? Yes, Michaela.
I'm actually kind of confused. Like, there are fusible ops, and then there are those ops which go into the like non-trivial case, right? So what happens to like if you do all this, and then in the middle of like your tanh ReLU or whatever, there's like an op that's like falls under the non-dense case. Like, does that make sense?
Yes, that's a great point. So to answer this real quick, Dynamo is responsible for graph breaking on non-dense. Yes, Hars.
Or so graph breaking is like one option, but I think the other option, right, is like even if it's not fusible, as long as it's like operating on dense tensors, you can still pass it down to a inductor without any issue.
But it wouldn't be operating on a dense tensor. It like requires the extra information in the nested tensor. Softmax is a great example when you're operating over a ragged.
Or yeah, but like that extra information can be represented as like dense tensors, right? Like multiple dense tensors.
Multiple dense tensors, yes. But
yeah.
You don't want them to be multiple dense tensors because that will tank the performance.
Or no, sorry. I don't mean by multiple dense tensors as an n dense. I mean like data and offsets. Like two dense tensors to be exact.
I feel like there's a mismatch between the question and the answer. One says non-fusible and the other says non-representable as dense. I think.
Or I don't understand what is non-representable as dense. Like, because the underlying data format, it's dense. Or like the underlying data representation is dense.
So Horace, yes, we can turn it into like 4 tensors. Sometimes we can turn it into 2 tensors. Sometimes we can turn it into 3 tensors, depending on how complex the shape is. But again, like I don't think we need that right now. Let's just focus on the simple case. And Ed's question was if the AOT dispatch changes that he suggested make sense. I think the answer is yes.
Okay.
Okay.
So we've got two options. I certainly think the graph break thing will definitely work and will be a pain to implement. And I suggest we discuss option 2 some more if you want to grill it. Dark Ritual?
Yeah, I had a question for the AOT dispatch proposal just above. You say treat them as proxy tensors to be traced. What is them in that sentence?
The nested tensor inputs.
4. Okay, and the second one as well?
Yes.
Okay, because I think
treat the buffers as proxy tensors to be traced.
Okay. Yeah. Okay, that sounds good then. And I guess we just need some. Like, I don't think we need to unwrap and rewrap all the time at the AOT dispatch level. We just need the nested tensor to, if I have a buffer that already exists, just use that.
Yeah, but
and it just happens that this buffer will be the proxy tensor.
That's already captured in Ed's proposal that AOT dispatch would rewrap only to call user functions or on output.
I don't think AOT dispatch should ever rewrap anything, is my point.
No, it does. It does this for AutoGrad too. It's
Well,
let's take this offline.
Yeah, sure.
It's a technical detail. Brian.
Yeah, I just wanted to highlight / confirm, at least in my head, like the difference between AOT dispatch for like Torch dispatch subclasses versus nested tensor. Or like the thing that's the same is that AOT dispatch takes a function that that takes in nested tensors and returns nested tensors and produces a graph that takes in dense tensors and returns dense tensors. So the like entry and exit, this like wrapping and unwrapping needs to happen. And then for Torch dispatch subclasses, the like translation from subclass to dense all happens inside of like the Torch dispatch function, where you're like given an op on from A10 on the subclass, you redispatch to another op on dense tensors. And then the only difference for nested tensor here is that instead of having this like giant translation in a Torch dispatch block or something, we just have like individual decompositions for all these different ops that nested tensors act on. And then it sounds like we're not going to cover all of the nested tensor ops, and then TBD if we like graph break in those cases or just desugar to dense tensors.
This sounds all right. I actually think there's not very much difference between a Python tensor subclass, that's Torch dispatch, and a C++ tensor subclass, which is what nested tensor is. They should basically be equivalent, except you get a dispatch key, so the dispatch key can help, but like that's otherwise the
yeah. And like a kind of related thing is like for implementing AOT dispatch, there's like it's like even if the format is the same of this idea of like a wrapper tensor desugaring to dense, it's like the way that's presented in our system, there's different ways to do that, like Torch dispatch, Torch function, func Torch transforms, and then also specific dispatch keys. And so there's probably like some work to think through like how to like handle all those different cases in a similar way.
Voss.
Yeah. So option 1 and 2 seem interesting in that I think 1 sounds like it gets us really far and then hits a block that like you have to fall into 2 to reconcile. At which point it feels like maybe we should have just done 2. I don't have a good idea of what the split is. Is it like 99-1? Is it 80-20? But option 2's plan seems a little confusing because it feels like you've sort of said, okay, we just need dense tensors, but actually we might need 2 of them or some other extra bookkeeping. And so maybe at that point, if there's enough use case for 2, would we just not make a new structure and pass that down with metadata and everything it needs instead of like trying to pack a bunch of extra bookkeeping into dense tensors? And then because now technically you're still only storing dense tensors, but now inductor does have to understand like, hey, these 2 are related in this like special way and don't use this one as data, which I guess I fail to see the benefit of 1 if we eventually have to put in the hacks in 2.
Christian.
And the analogy here is that when you have contiguous tensors, you don't need the strides, right? So you could technically like remove that metadata. Or if you are just looking at unary operations, you would, and it's a contiguous dense tensor, you collapse. So you don't even like necessarily need the sizes. You just need the number of elements, the amount of storage used. So it's similar here. We are introducing a structure that gives the user the ability to construct more complex shapes than what we currently have. And one category of shapes can be expressed with tensors with 2 tensors effectively. Just
go ahead.
Yeah, just like one category of Torch tensors can be expressed without having strides.
There's one more thing that I want to add here, which is that basically, if you're going to pass down a structure with all the metadata, that's basically passing the nested tensor directly. But we said that long term, that's what we want inductor to do. So there's no problem. Like, so the way we're going to get around the block from option 1 is by then just teaching inductor.
Yeah, and that's kind of what I was getting at. Okay, cool. So that actually seems quite reasonable. So we do 1 for now, but then eventually we do have end-to-end like nested structures.
Yes, it's just supposed to be like getting us there.
Cool, that makes sense.
Okay.
Bite-sized work.
Any other comments? I have one last comment, which is one of the examples Mengshi gave me about a fusion they want to do is there's a packing operation that gets you into Jagged Tensor in the first place, and it is often profitable to fuse that with the pointwise dense operation that happens afterwards. So that's where dynamic shapes will come in handy. Besides just like these fragments want to be dynamically sized because you're going to be varying how big the nested sequence is. Some food for thought for the room. Okay, thank you everyone. We're at 2. See you all next week.